Hi everyone, my name is Rahul Sequera and I'm the simulation engineer here at LaunchTech. Today I will be presenting to you a webinar that is based on improving aircraft performances with CFD. And I hope you find this webinar very intriguing as we have a lot to discuss about how Dassault Systems has heavily invested on its CFD tools for the aircraft, aerospace, and defense industries. The webinar will be 35 to 45 minutes long as I'd like to keep the panel open for questions. So before I go straight to the topic, I'd like to introduce ourselves as LaunchTech. Primarily, we are Dassault Systems' main software distribution partner. We mostly distribute the SIMULIA portfolio, which compromises of FEA, CFD, and EMAG analysis. For those organizations that have short-term needs of simulation tools, we also do provide technical consultancy for them. Along with that, we also provide software technical trainings for those who require them in order to fully understand the true potential of Simulia's tools. And then we foolproof their knowledge in these tools with the means of certifications. So I always recommend our valued clients to get themselves certified when they have the time to do so, as this might unlock potential for them to further boost the productivities and outputs of their operations. A bit about Simulia in general. Simulia is comprised of one of our main tools, which is Abacus. That is an FEA multiphysics solver, which is used to solve both static general analysis and implicit and explicit dynamics. Abacus now is being complemented with optimization and fatigue analysis tools by the means of EyeSight, Tosca, and FESafe. For those organizations that deal with large assemblies with many subparts and would like to calculate the dynamics of it, we do have an articulated system dynamic tool called SIMPAC. And then this tool can be used to export the physics either back to Abacus for further evaluation or to our CFD solvers, which is the PowerFlow and XFlow solvers. And finally, we also provide a computational electromagnetic suite in the form of CST Studio. So let's talk about how XFlow or how our CFD solver is used to achieve the objectives for improving the aircraft aerodynamic performances. DS has always taken our valued clients' feedback with the highest priorities. And we have realized that the major objectives we need to achieve in order for them to be satisfied with our products is one is that they require a simulation driven design to achieve higher fuel economy and range. They are also highly demanding of transonic and supersonic algorithm and CFD solvers, as the classic CFD methods are struggling to keep up with the accuracies required. In order to meet certification requirements and compliance, they are also in need of a tool that reduces noise emissions from aircrafts. And finally, with the combination of these, they are hopeful that these can ultimately reduce and maybe even replace physical testing. So XFlow has been highly developed in order to meet these objectives. And today I'll be giving you a brief objective about why aerodynamicists need Simulia XFlow in their organizations. So what is Simulia XFlow? Well, it is a CFD solver that is based on the modern lattice Boltzmann technology, which is unlike the meshing based, it's a particle based method, and it uses a high fidelity of prediction to solve transient flows. Because of its algorithm and the nature of its algorithm, it's actually made LES more affordable to solve. Coupled with a user-friendly graphics interface, it actually helps users to use a reduced time in order to set up their CFD solutions. The beauty of XFlow is that it includes an adaptive refinement algorithm. So what it does is it automatically refines the wakes and the interfaces of the paths depending on their positions. And the last important thing is that XFlow is also equipped with the Mall model large eddy simulation turbulence model. So what it does is that with this model, it's able to provide high resolution results for complex geometries and even complex dynamic flows. So why does XFlow use the lattice-Boltzmann method? Well, the lattice-Boltzmann method is able to solve flows at even the mesoscopic level. So this is a scale below the macroscopic, which the Navier-Stokes usually use. Because of this accuracy, it's able to compute the streams and collision of discrete particles in those lattices. And these lattices, as I mentioned, is highly adaptive during the computation. So they move along with the geometry according to the current position of the geometry. As it is an inherently unsteady model, it actually complements very well with the LES turbulence models, unlike other solvers, which actually requires constant communication with the LES turbulence model in order to compute the parameters it needs to. So this actually takes computation time. Because of these, it's able to consistently provide accurate local eddy viscosities and near wall behaviors as well. As you can see with the images on your right, the mesh is highly refined to follow the wakes and to refine especially at those wake regions and the boundaries of the geometry. So what is the scope of the lattice-Boltzmann method? Well, because of its high accuracy with transient solvers, they're able to solve transient aerodynamics really well. So this allows them to accurately predict the lift and drag predictions of highly complex maneuvers like this Cobra maneuver this aircraft is doing right now. It's also able to provide better aero design and styling because of its accurate solver. As I mentioned, a lot of CFD analysts require acoustic solvers in order to meet noise level reductions, and XFlow actually is equipped with an acoustic solver to meet this objective. XFlow, other than the single phase model, is also equipped with the free surface and multi-phase flow models. So what it does is that free surface allows CFD's analysts to actually solve simulations like this plane ditching onto a water body to understand what really happens to the plane during these situations. It also helps with understanding how jet engines operate with a mixture of fuel and air during its operations. And I'll show that simulation to you in a further slide. Lastly, XFlow is also good in solving complex fluid structure interactions, especially those with the real moving parts. For example, like the jet engine, it's a highly dynamic machine, but XFlow is able to solve them really well because of its high refinement strategy. So let's look further of how XFlow actually achieves the objective of higher range and fuel economy for aircrafts. One example in how it achieves this is through the continuous study of landing gear systems. As you all know, when the landing gear system is deployed during the landing phase, which is the longest time when it's being deployed, it actually introduces a lot of drag to the overall structure of the aircraft. As I mentioned, XFlow's near adaptive refinement strategy captures the wake fields very accurately, and because of these, they're able to calculate the drags produced. These simulations are important because the results can then be used to input it into further design improvement cycles or into an optimization strategy to hopefully reduce the drag increase. Sorry, hopefully reduce the drag created by these landing gears and ultimately increase the fuel economy of aircrafts, especially during landing. Another application I want to share with you is de-icing or ice shedding. As you all know, when ice builds up on the aircraft, it actually increases the drag and reduces the overall performance of the aircraft. CFD analysts need to understand how these de-icing methods are being simulated, and they cannot afford experiments to do so as they are expensive. So how XFlow manages to achieve this is that it actually uses its own thermal properties along with the CFD solutions. And then it even co-simulates with Abacus in order to include the mechanical properties like the ice brittle cracking formula. Together, this is how we want to demonstrate the power of the SIMULIA portfolio when used together. Another important factor uh, that achieves the higher range and better fuel economy is the necessity of understanding flight control stability. As you all know, when the nose pitch or the flap extension is being made, they actually are being affected by the turbulence of the surrounding atmosphere, and that can affect the performance of the aircraft. So XFlow's transient and LES turbulence solvers are used where engineers can actually calculate those intermittencies in the aircraft stability during clear skies or even turbulent weather conditions. Because of this, it's able to even seamlessly post-process because XFlow has a very good post-processing tool to view those vorticities and adverse pressure gradients. As you can see in the graph at your right, you can see when the pitch angle is being increased or decreased, XFlow actually accurately calculates the pitching moment very well, especially when it's been affected by the turbulent scenarios. The same thing goes with when the flaps are being deployed. Because of turbulence, it's able to capture those intermittencies in the stability of the aircraft. And as I mentioned, with jet engines, they're also able to use the multi-phase flow in order to understand how the aircraft operates under its cruise conditions. And this is some of the ways in how XFlow is being used to improve the range and fuel economy of aircrafts. Let's talk about the need for transonic and supersonic flow solvers. As you all know, as aircrafts, especially fighter jets, are getting more advanced, CFD analysts require a tool that's able to accurately solve maneuvers, especially these maneuvers in simulation. As you know, these are expensive to experiment them. Experiment them. So they require transonic and supersonic flows, and XFlow actually have these sophisticated tools in order to solve them. So because of this, it actually makes these aircraft maneuverability techniques very easily to solve, and it becomes a necessity for CFD solvers to use. Because of the implementation of XFlow's algorithms in using X enforced laws or rigid body dynamics, you can actually couple them with the supersonic solvers to simulate the Cobra method as this simulation shows here. And if you see the graph, XFlow is actually able to simulate accurate flight envelopes of these fighter jets when compared to the experimental results. We took it one step further to create a simulation of a projectile trajectory, and we've even included the thermal solvers with it. And as you can see, as the projectile reaches transonic speeds, the CFD solver is still being able to produce accurate experimental results with very low XFlow error values. So, and obviously, you know, as aerodynamicists need errors to be less than 3%, XFlow errors are still at that acceptable range compared to other CFD solvers. We took it another step further by using rigid body dynamics in order to understand how the projectiles separate when they are detached from the main attachment. And as you can see, XFlow is able to solve these simulations really well. Of course, we cannot talk about transonic and supersonic flows without including the shockwave experiment. As you can see, the shockwave experiment was done using not only XFlow's a default function, but also user input functions into the solver. These function data can also be written using Boolean operators and conditional command lines. And as you can see with the post-processing in the right, XFlow always allows seamless post-processing using multiple stacked windows. They are highly customizable. And you can even compare the function over time with the results or the contours, as you can see here. Another experiment that a lot of CFD analysts need is the understanding of wingtip speeds, because we know that aircrafts move at transonic velocities, but the actual wingtips reach the supersonic boundaries. So we wanted to test how effective the XFlow algorithm solves uh, supersonic flows, and we've taken the case study of an aircraft traveling at 0.85 Mach number with an angle of attack at 3 degrees. So XFlow is able to simulate this, and it's able to predict that the CL of that aircraft is a bit higher than the experimental values. But then you can also see that the drags also increased according to that. So because of this, it's actually able to solve the performance very well. And since we've got the validation results of these high Mach number simulations, we can actually see what the Mach numbers are at such scenarios. And as you can see that the suction side actually experiences a lot of supersonic flows, while the pressure side have areas of supersonic flows, which are essential for CFD analysis to study on. Let's now talk about reducing the noise emissions of aircrafts. As you all know that jet engine noise is loud and it is discomfort for uh, many who are being passed by it. There are a lot of stringent regulations that are required in order to control those noise levels. So aircraft engineers or jet engineers can also use XFlow's algorithms in order to solve these acoustic analysis. And as you can see here, these XFlow simulations make it much easier for them to pass these regulations and certifications. Finally, we also talk about the reduction or possibly the elimination of physical tests. As you all know, simulation is no longer a validation tool. Many industries are benefiting from its simulation-driven design processes as well. And ultimately, because of these simulation-driven designs, we share Dassault Systèmes' goal to significantly reduce the number of physical tests and ultimately even eliminate them, as for the aerospace industry, they tend to be very expensive. So one solution in how we try to do this is we combine the power of all SIMULIA's physics to simulate a seamless simulation experience for engineers and scientists, and that's by coupling their structural, fluid, and thermal analysis, even multi-body analysis if needed. So how we've done that is that XFlow has seamlessly connected to co-simulate with Abacus and SIMPAC. And I'll show you some examples of how this is done. So here's one example where the landing gear panel on this aircraft is broken away. And then Abacus determines Abacus determines when it breaks according to the speed of the airflow. And XFlow then uses its algorithms to solve the trajectory of that landing gear once it's being detached from the aircraft. Another example that can be used is a parachute deployment, where Abacus is used to actually solve the stress of the parachute, and the CFD analysis is also used to solve the airflow of the parachute once it's being deployed. And with that, I will now show you a live demo of XFlow and how it is used to solve high dynamic flows like an aircraft simulation. So I'd like to introduce you to XFlow's GUI. As you can see, it's very clean and intuitive, and its models are orderly placed in order for simulation engineers to have a seamless experience with it. Within XFlow, you have 5 different tabs to solve: the environments, material, geometry, simulation, and the post-processing. So it's very simple. With 5 steps, you can solve a CFD problem intuitively. I've already imported a geometry of a CATIA part of an aircraft wing. And I will now be showing how XFlow can be used to manipulate the position of the aircraft wing along with the wind tunnel. So the first option you will be receiving is how you solve that kernel, whether you want to use 3D analysis to solve the whole domain, or you want to take a section of that domain and solve a 2D flow of it. For this case, I'd like to take the 3D analysis of it. The flow model is then asked, which you can choose either you want the single phase, free surface, or the multi-phase. Since I'm only dealing with air, I'll only deal with the single phase solver. Uh, the choice of choosing external and internal depends on the type of flow. Since I am more interested of the airflow around the boundaries of the aircraft, my simulation is more of an external rather than an internal flow. Internal flows are, for example, like pipe flows. If you want to understand the flow of water inside a pipe, that is an example of an internal flow. So I'm choosing an external flow for now. And for the simplicity of the model, I don't think I need any energy models. I'm going to stick with the isothermal model. As I mentioned, you can even add turbulence models into it, and I will add a wall adapting local eddy, uh, an eddy method, as that works very well with XFlow. So I'm going to click that, and I will give a coefficient of about 0.5. Again, because of the simplicity of model, I know that it might be a bit more expensive if I add turbulence generation. That means that I can actually add an inlet with turbulent velocities in, and these are very crucial for CFD engineers who are dealing with airflows at cruise altitude, as there are certain regions of turbulence that can be created. But for this simulation, I'm going to switch it off. And you have other simulations, including co-simulation with Abacus or with Nastran or even SIMPAC. You can use the wall function time filter, which I'll not be using now. And then you can even add your gravity if you want. So for example, since this is a virtual wind tunnel, you could add a gravity boundary condition if you want. I'd rather not have it for the time being. And then you can even dimension the exterior parts of that wind tunnel according to your CFD analysis. So for me, I think the best parameters I'd give is I'd like to position the wind tunnel to be at 15, 0, and 15. And as you can see, that XFlow does it really quick along with the dimensions of it. So I think I will give this about 60, 20, and 30. And I feel this is an adequate region to do my CFD flow. And since I want the inlet to have a high speed, I think it is fair that I give it a velocity of 75 to understand the takeoff conditions of this wing, as the main objective for my study is to understand the takeoff of this aircraft wing. The second model is obviously to model the material properties of the air model that is traveling from the inlet to the outlet. So I'd like to start off with just keeping the molecular weight as it is, and maybe changing the reference density to something that is representative of the real world simulation. So that's 1.1845, which is the same reference density as probably 25 degrees Celsius atmospheric temperature. I'd like to even have a reflective viscosity along with the operating temperature. So I'd keep that to be about 1.8444 E minus 5. And then I'd keep even the thermal conductivity towards the reference temperature as well as the specific heat capacity. So with this, I have effectively modeled the aircraft to be moving at real world conditions. The next tab is to then manipulate the position of your geometry and whether you want to add rigid body dynamics or you want to enforce it for now. So in this case, I have already imported an IGES format of an aircraft, which can then be used to simulate the airflow around this geometry. Uh, as a guide, I'd always recommend that you keep your the geometry's boundaries closed. Don't open a geometry, as the air can actually go into the aircraft and actually spoil the results because of those open holes or unfilled gaps. So in this case, I would probably keep the geometries to be around 90 and 165 as the orientation of my aircraft. And as you can see, I have positioned to be exactly where I want it to be. Since I do not want to deal with the adaptive refinements for now, since those are expensive, I would keep my behavior to be fixed. And since I know that aircraft grade smoothness is 1E minus 6, I'll keep it at that height. So wall roughness is now kept at that height. And this effectively, completes the geometry process of that aircraft. I've kept the scale as 1 because I've already imported the CATIA part in the form of meters. Finally, you are then asked to put the parameters or edit the simulation parameters as per the uh, capabilities of the machine. So since I do not have an extremely powerful machine, I will use, let's just say, a simulation time of 5 seconds. And I'll keep the current time as 1 for now. But then the resolve scale, I'll also increase that to 1. And and for the sake of an accuracy improvement, I think I will refine my lattices near the walls of near the walls of those parts. So I'll keep a near static wall, and let's just say I would like to have it around 0.125. So that's 10. That's basically 10 scales lower than the original resolved scale. So at the geometry, the mesh will be refined 10 times further. No, it will be actually refined 3 times further, because if you do 1 divided by 2, it becomes 0.5 divided by 2, 2.5, and then, yeah, 1.25. So it'll actually be refined 3 times, 4 times further. My bad. Uh, After that, you can just give the frames frequency for it. So I would like to give a frames frequency of about 25 hertz. And I'd like to save the frames from the 0th second itself. And you can then you can then ask XFlow to save some files. So for example, I like to save some of the markers, and I like to even save a Q criterion output. And this is basically how quick it is for XFlow to complete that how quick it is for users to complete an XFlow pre-processing. All that's required now is, if you're happy with the simulation, is just to run the simulation, start the computation, and and then the CFD solver will then compute from 0 to the 25th frame. So I won't do that now because I already have a ready simulation for this, and I'll show that. So as you can see here, the simulation is ready because the frames have been simulated before this webinar. We can now go through the intuitive post-processing tool where you can firstly see the domain structure or the lattice structure of the aircraft. So if I view that, you could see that the lattice here is at 1 meter, and then close to the boundary, it's been refined 4 times further near the aircraft plane. So this is how XFlow automatically refines the near wall lattices. And then if I want to now show the velocity distribution along the plane, I can do that as well. So I then go on to the 3D fields, and then I click the velocity. And if I go through as the time, you can see that the simulation is now being processed at those time steps. And if I want further cutting planes, I can even do that to give more accurate simulations. Uh, I'll just switch off the volumetric fields for now, and I'll keep the second cutting plane. And as you can see, I can now simulate the flow of the air at those times. And if I want to move those planes, I can do that as well. I can do it like I can just click it and then move it up. As you can see, it's very intuitive for a CFD analyst to solve these types of flows. So makes it very easy for them to understand the drag and the lift coefficients. Speaking about those coefficients, you can actually solve them. You just have to click the new functions viewer. You'll then be given to the functions tab where you can where you can actually understand uh, 1 minute, where you can understand uh, the drag and lift of the aircraft. There it is. I then have to just go into shapes. I go into the Boeing 737 wing, and then I check the drag coefficient, which is CX. As you can see, this is the drag coefficient. This is the lift coefficient of the aircraft, and then you can then create further functions in order to get the aerodynamic performances of that aircraft. So this is how you basically solve aircraft dynamics at high speeds using XFlow. Now to conclude with the webinar, XFlow is actually a dedicated CFD solver that uses the LBM method to solve all speeds of complex flows very well. The capabilities combined with the possibilities to solve these in high-speed aerodynamic applications with high levels of accuracy parameters like drag, lift coefficient, skin friction, and vibroacoustic make it a very ideal tool for uh, aerodynamicists and aircraft engineers to use XFlow. And if XFlow is being used, then industries are obviously achieving those four objectives in order to exceed the competition, which is the continuous improvement of performances and fuel efficiency. They can simulate aircrafts at supersonic and transonic flows. They can even achieve reduced noise and vibroacoustic emissions in order to meet those certifications. And finally, they can even achieve significant reductions in the need of physical testing with XFlow. Now we're still running a promotion that is valid until 31st of July. So for those who are interested in learning more about the XFlow algorithm and who would like to have, a full in-depth in-depth course in XFlow, PowerFlow, Tosca Fluid, and EyeSight, we are running a promotion that costs only 204 euros for a yearly license, and with that you get 10 courses that involve these four components. So I would recommend those who are really interested in exploring XFlow to take the advantage of this great offer. With that, I conclude our webinar, and right now the panel is open for questions. Uh, I'd like to thank my audience for watching the webinar. I hope you really found this webinar very intuitive, and if you have any questions regarding this the CFD tool, I'm open for the questions. With that, I conclude the questions panel. And again, I hope you really enjoyed the webinar. And if you have more if you require more information on XFlow or its other CFD tools, please contact us on the emails displayed on your screen. Thank you for attending this webinar.